Welcome back to part 2 of section 5.5, row space, column space, and null space. Now, I'm going to talk about the null space here in a minute, but I want to draw an analogy. It's an imperfect analogy, but at least hopefully it will give us something to hang our hats on. So I want you to find the principal solution of sine of theta equals 1. And you may remember that the sine function repeats itself of period 2 pi. Okay. And the principal or primary solution is right here at pi halves. But, so we're going to write theta equals pi halves. And if you were to pull out your calculator and try to solve this by doing theta is equal to the inverse sine of pi halves, or sorry, inverse sine of 1, you would get pi halves. Okay. Now, we remember from our days in trigonometry that that's not the only angle that I can stick into the sine function and get out a 1. In fact, I'll get it at pi halves, 9 pi halves, okay, and I'll have infinitely many solutions here. In fact, we wrote this as theta equals pi halves plus 2k pi, where k was an integer, okay? So basically, this just did extra spins on the unit circle, but still put us up at the top at pi halves. Something to note, though, is, what do you know about the sign of 2k pi, where k is an integer? Well, it's 0. So what I want you to do now is take this A matrix. I want you to find and label a basis for each of the row space, column space, and null space. I'll get you started. So the row vectors are 1, 3, 5, 0, 2, 4, and 2, 1, 0. So what do these guys cover? Can you find a basis for what they cover? So we need just enough vectors to cover it, but no unnecessary vectors. So find a basis for each of the row space, column space, and null space in this situation. And we'll pause the video so you can have time to do that. Okay, let's see what you were able to come up with and compare notes with what I did. So we took our row vectors, and we noticed that we had 3 vectors in a 3-dimensional space. Let's check to see if any of them are linearly dependent. So I go back to my definition of linear dependence, and I do a linear combination. So a scalar multiple of row 1 vector plus a scalar multiple of row 2 vector plus a scalar multiple of row 3 vector, and set that equal to the 0 vector. That creates for me this system, which then, if I RREF, turns into this guy right here, which tells me that the 3rd vector can be written as a linear combination of the first 2, so he is unnecessary. And that leaves these two, 1, 3, and 5, and 0, 2, 4, 7. Since there's only 2 vectors, I can easily check for linear independence by checking to see if one is a scalar multiple of the other. And since neither is a scalar multiple of the other, the basis for the row space, so they're linearly independent, and what they span from the rows of the matrix is covered by these 2 vectors, which would be, in essence, a plane through the origin. Okay. We do something similar for the column space. So we take our column vectors, okay, and we form a linear combination to see if any of them are linearly dependent. That sets up a system which we RREF and find out that the 3rd vector can be expressed as a linear combination of the first 2. So he's in a sense unnecessary. He doesn't contribute anything to the span. So I could then say that the basis for the column space is the vector 102 and the vector 3, 2, 1. And sometimes I write them as column matrices like this, but sometimes you'll see them written as 1, 0, 2, but then the transpose to help us remember that these things are actual columns. Okay. Now for the third one, the null space, it's what the matrix sends to 0, the null vector. And we've actually already solved this system. You'll notice that this is the A matrix, and here's the 0 vector. So we're solving for AX equals 0 here. So I'm not going to redo the work if I've already done it. And so the null space will be given by the vector t, -2t, and t. And if I factor out the t, the basis for the null space, what this A matrix will send to the 0 vector is 1, -2, and 1. Hopefully that's made sense and you got the same things. Let's go ahead and take a look at what's happening here. So if we take a look at our row vectors of 1, 3, 5, 0, 2, 4, and 2, 1, 0, you'll notice that they all live in the same plane. So they're coplanar. They're a two-dimensional subspace of three-dimensional space. So the third vector, the W vector, 2, 1, 0, is linearly dependent. I can cut him out and I can still make everything that I need to in the plane using my U and V vectors. So the row space is a plane through the origin spanned by the vectors 1, 3, 5 and 0, 2, 4. Okay. What about the column space? So the column space is, we had 1, 0, 2, 3, 2, 1, and 5, 4, 0. You'll see that those also still stay in the same plane. So and we found out that the third vector can be expressed as a linear combination of the first two. So I could use those first two, the 1, 0, 2, and the 3, 2, 1 vector to be a basis for what the column vectors can cover in the space. Okay. Another thing to note is if I create the vector t, -t, 2t, and t, that will form the parametric equations of a line where x equals t, y equals -2t, and z equals t. And that again itself is a line through the origin, which under standard operations is a subspace of R3. And we'll see something special about this null space in relationship to the row space a little bit later. But let's go back to our paper. One thing that I noticed while I was making this is I tricked myself just a little bit here. If I didn't want this to have any fractions, so I made this be 2t, so this actually should have been -4t here. But that still means that the third row vector is linearly dependent on the first two. So what I want you to do in preparation for the next video is to let B be the RREF of matrix A, find out what that is, and then create a basis for the row space, column space, and null space of this new matrix B, and we'll compare with what we got up here. So see you in the next video.